So before we look at this problem here, there's one thing that I want to establish. Suppose that the pen is home. If I move away from home, then my velocity is positive. If I stop, my velocity is 0. And if I backtrack back to home, my velocity is negative. So going away has a positive velocity. Coming back has a negative velocity. Now, looking at this picture here, I found this online, and this models a particle's position versus time. Here on this paper, I'd like to graph the particle's velocity versus time. There is an idea in calculus that is called a derivative that would make this process here much simpler, going from position to velocity. If I use the derivative from calculus, it would make this simple. But I'm going to assume that at this point, you guys have not been introduced to the idea of a derivative. So I will do this in a more elementary fashion. Here is what I would do. I am going to make a time drt velocity chart. And let me make some columns here. And I don't know yet how many rows I will need, but let's see here. I'm looking at this graph. Here I have one chunk, and here I have the next chunk, and here I have another chunk, and then I have this piece here. So I have I have 4 snippets. So let me create 4 different rows here. So something like this. Now, the first time frame goes from time 0 to time 1. This first little chunk from 0 to 1. So I'm gonna say 0 to 1, and then I would eventually go from 1. So from here to here, that's 1 to 3. So I'm gonna go 1 to 3. And then this middle piece goes from 3 to about 4.5, let's say. 3 to 4.5. And then the last piece goes from 4.5 to 6. Now let's worry about this piece here. Distance equals rate times time. So let's go back to 0 to 1. At 0, my position was 20 meters from home. After 1 second, I am still 20 meters from home. So I did not move at all. I was frozen from 0 to 1. So the distance that I covered was 0 equals R is the rate, how fast you were moving. I don't know how fast I was moving yet, so I'll just call it R. T is the time. How much time are we talking about? From 0 to 1, that's 1 second. So this is times 1. And so this is 0 equals R times 1 is R. So my rate is 0. And when I say rate, I really mean the velocity. So my velocity is 0. And that makes sense because I didn't move. I didn't go anywhere. I was the same distance from home here as I was there. Now, from 1 to 3. So at time 1, I was 20 meters from home. At time 3, I am now 60 meters from home. So I've gone very, very far from home. But exactly what kind of distance did I cover? 60 minus 20, right? 60 minus 20, that's a distance of 40. I covered 40 meters of ground from 1 second up to 3 seconds. So let's see. So D equals RT. The distance covered was 40. The R is the goal times, what's the time? From 1 to 3 seconds, that's 2 seconds. And let's solve for R by dividing both sides by 2. So R would equal 20. So my velocity is 20 meters per second. And back here, 0 meters per second. It's meters because it says meters there, right? And seconds. Now the next one, 3 to 4.5. From 3, at 3 seconds, 60 meters from home. At 4.5 seconds, I'm still 60 meters from home. So I didn't move at all. Maybe I was tired and I needed to take like a little timeout, like a little break or something just to catch my breath. So from here to here, the distance covered was 0. So distance is 0. The rate, I don't know. The time is 1.5 seconds because from here to here is 1.5 seconds. If I divide that into that, my rate again is 0. So 0 meters per second. And let's finish this off. From 4.5 to 6, so from here to here. So what's the distance covered? Notice that at 4.5 seconds, I was 60 meters from my house, so I was really far away. But then at the 6-second mark, I was only 20 meters away, so I have come back closer to home. So my distance, for D, the distance is actually going to be negative 40. And I'll tell you why it's negative. Because you're supposed to go this distance minus that distance. This distance here is 20. And then that distance here is 60. So it's 20 minus 60, which is how I got the negative 40. And essentially, anytime you see that the position is coming back down, you can expect your distance to be negative, along with the velocity. So let's see. So this equals R. And then the time from here to here, that time is 1.5 seconds. And I'll divide by 1.5. 1.5, those are gone. So my rate is, if I divide that by that, it should be about, if I round this, it's about negative 26.6 bar meters per second. So that's my velocity. And let's see, so this is just a chart. Now let's use this chart to make a graph. So here I have my time versus velocity graph. Time is in seconds, velocity is meters per second, and I have the same time frame as this graph here. And so let's graph this data on here. So from 0 to 1, my velocity is 0. So from 0 to 1, my velocity looks like this green, like that. Now let's see. From 1 to 3, so from 1 to 3, my velocity should be at 20. So from 1 all the way to 3, my velocity should be 20. So I connect the dots, like that. And then from 3 to 4.5, so from here to about there, my velocity is 0. So like that in green. And then from 4.5 to 6, my velocity is negative 26.6. So about right here to about right there. And then it is very customary to sort of draw these vertical beams that join the graph. That's just what we do very often. And I suppose that I'll just leave it hanging there. So this is an example of how to go from position to velocity by means of a chart. So here's one way of doing a problem like this. And also, by the way, this position graph, it only had line segments. There were no curves here. If the original graph had had curves, then I don't know if we would have been able to use this, because DRT is really for objects that are linear, like this, like lines. But if there had been some sort of a curve to it, then this really would not have been an option. We would have needed to do other types of math to go from position to velocity. Oh, but also real quickly, one thing I want to throw at you, somewhat of a shortcut, and that is this. Recall from like freshman year of math, the idea of a slope, how that if you have a line with a horizontal slope, the slope of this is 0. If you have a line that is like this, the slope like that is positive, like the rise over the run, right? The rise over the run would have been positive. Something like this, it's more of a fall, so this slope would have been negative. And that's exactly what you can see here. Watch. Here, that had a slope of 0, which is why the y-coordinates here were 0. Here, if you go rise over run, the rise is 40, because from here to there, that's 40. And the run is 2 from here to here. So it's rise 40, run 2. 40 over 2 is the 20 that you saw. So that's why this piece here, it had a slope of 20. And the slope manifests itself here as a y-coordinate. The same here. This slope is 0, which is why the y-coordinates are 0. How about here? What was the slope? Rise over run. This isn't even a rise, this is a fall. And the fall was from here to here, that's 40 negative, and the run was 1.5. And if you divide, that's exactly what we did there. That's why this was negative, because here the slope becomes a y coordinate there, in this case like negative 26.6 or whatever. So the idea of finding a slope and turning the slope into a y coordinate, that is what we call the derivative, which is what I mentioned at the start of this video. So if next time you do a problem like this, from position to velocity, you can make a chart, or you could just calculate the slope of the individual segments and turn the slopes here into y coordinates there, because that's exactly what we did by means of a table. So I hope this helped. And as I said a moment ago, maybe we'll make another video soon that has a slightly different scenario.